Hi guys, this is Steph with homework 3 number 5, which says, prove for all A is an element of G, the order of A is less than or equal to the order of G. So in our case, the less than or equal to really means less than or equal to. It doesn't mean subgroup. So first thing I did was I wrote out, well, what does the order of A mean? The order of A means that A to some number n equals the identity, so the order would be that number n. The order of G means the number of elements in G. So for this proof, there's two cases. Either the order of G is finite or the order of G is infinite. The order of G is infinite is considered trivial, but we'll start with the non-trivial case. So case 1, order of G is finite. Okay, so if the order of G is finite, that means that let the order of G equal n, where n is some member of the natural numbers. So we're going to choose an element. Choose an element A is a member of G. So if we list A squared, A to the third, we can keep going until we get A to the n plus 1. So if we do that, we know that two of those elements have to be equal because G only has n elements, as we stated in the top, and this has n plus 1 elements. So we know that two of those have to be the same. Now, that could have happened in the beginning, like A2 and A4 could be the same. So we don't necessarily have to go up to A to the n plus 1, but if we do go up to A to the n plus 1, we ensure that two of them must be the same, so we cover all our bases. So let's write that out. All right, so here I just wrote out everything that I explained. So let's keep going. Okay, so we know that two of them have to be the same, so we can say that sum A to the k must equal sum A to the l, where 1 less than or equal to k less than or equal to l less than or equal to n plus 1. So we can arbitrarily choose that k is less than l. Hold on. They should be, this one should be a strict inequality. All right, so we can arbitrarily choose that k is less than l. You could choose l is less than k instead, it wouldn't matter. We know that k has to be less than or equal to 1 because we start with just a in our list, so we start with a to the 1. And we know that l has to be less than or equal to n plus 1 because that's the last thing that we have in our list of a's. Okay, so I can multiply both sides by the inverse of a to the k. So I get a to the negative k, a to the k equals a to the negative k, a to the l. So anything times its inverse just gives me e. So e must equal a to the negative k, a to the l. So we can combine the exponents and we get e equals a to the l minus k. All right, so we know that the order of a is whatever power you raise it to get the identity. So that means that the order of a equals whatever l minus k is. And we know that that has to be less than or equal to n plus 1 minus 1 because we know the biggest thing that l can be is n plus 1. And the smallest thing that k can be is 1. So we know it has to be less than or equal to the biggest minus the smallest. And we could simplify that to just n. And we know, because we stated it before, that n is the order of G. So, therefore, we know that order of A less than or equal to the order of G. So that was case 1. Case 2 is the trivial case, where the order of G is infinite. All right, so it's considered trivial because if the order of G is infinity, then no matter what the order of A is, it must be less than or equal to infinity. That just makes sense, right? So that's it. So here is the proof. You can see it all in one window, and that's it. I hope that made sense.